All right, we're going to look at Shigley Chapter 13. This is kind of a introduction to gears, and there are a few equations that we'll look at in here. Most of what we'll do on gear design will be in another chapter right after this, but this gives you an introduction. We're not going to be able to go through all of Chapter 13. It has a lot of different gear types and the shapes of different gears. We're going to stick to spur gears and involute tooth profile spur gears. That's the most common these days. There used to be just, I guess, an assortment of gear teeth, but involute is the most common type now. And, 90-something% of spur gears are involute tooth. So I guess we need to talk about what involute tooth shape means. The idea is that you have a smooth transfer of torque from one gear to another. So normally there's at least one gear interfacing with one other gear. Sometimes there's more than one. We'll look at a scenario here where there's one gear interfacing with three gears. And that's not uncommon. It's just, at least there's two gears meshing together. And you want the teeth of one gear to interface with the teeth of the other gear. Usually you call the smaller gear the pinion and the bigger one the gear. So a lot of times the pinion is a smaller one. So this pinion and gear, you want them to transfer torque smoothly. And the involute tooth profile does that. Now your book goes through trying to describe what that might look like. They have this diagram. This is figure 13.8. And what they're describing here is this circle called the base circle. That would be a circle that's part of the gear. So it is, inside the piece of the gear. It's not an actual circle. It's just a descriptor. And what they're showing is that there's a string wrapped around here, and it's coming off at these different tangent points, A4 through A0. And they've got a common point marked on this string, and they're basically plotting these points. So I've kind of done a similar thing over here with a roll of tape. To me, tape was what I had, so we're going to use tape. Let's get this stuff out of the way, though. Here's my roll of tape. Got a pencil attached to it, and so the outer circumference of the tape would be the base circle in this diagram. The pencil would be the little dots here, and then the tangent lines would be the tape as it comes off of the roll. Now notice I got to readjust this to get the pencil lead just right at the end because it was giving me problems there. Alright, so I think we're good now. Alright, so what you would do is you would unroll a little bit of tape and mark. You want this to be a tangent line. Unroll a little more, you want a tangent line. Unroll a little more, I want a tangent line there. Unroll a little more, I want it to have a tangent line. Maybe unroll a little more, there it looks like the tangent line. Unroll a little more, tangent line. And what I'm creating is a little series of points. Now I've made them longer so that you can see them. In fact, let me darken them up. So I had a point basically there, 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 there. And if you keep going, you would get this curve, that's going to create a certain shape. That shape is the involute shape. And it's not that you're just, just like ripping it off of here and creating that curve. That would be, more or less like a circle. So you have to have it, the string or the tape or whatever, every time it comes off, it has to create a tangent line to the base circle. And then that point that you plot creates the involute profile. And so that shape, basically it ensures that you have this common point that is on a tangent line at any point, wherever the tangent line is to the circle. You've got a common point. The pencil has traced out a profile, and the pinion and the gear would have the same shape teeth on them. And they have to have the same size teeth on them, so you can't have different size teeth interfacing with one another. So it would have the same shape, and that would ensure a smooth torque transfer from the pinion to the gear, or vice versa if you go another way. And so that's what involute means. Now you could have all different shapes of teeth, and you would get different, torque transfers, but you would not have smooth. You would hear this surging sound in your gears with non-involute teeth as they kind of accelerate and decelerate every time a tooth makes contact with a joining tooth on the pinion from the gear. They would surge, so it'd speed up and slow down, speed up and slow down, speed up and slow down, and it would sound. If you've ever heard that sound, which you don't really hear anymore because most teeth are involute, then you would recognize it. But it's this accelerating and decelerating of the torque transfer between pinion and gear, and you don't really want that. That's generally not something you want to happen. So most teeth on gears these days have this involute shape. There are also a lot of other terms. Let's see. Is this? That's too confusing. This one looks good. So here you've got the pinion, again, the smaller gear, and you've got the gear, the larger of the two. You can kind of see some of their teeth profiles on here. Now, these, let's see if we can make this larger so we can zoom into that. These, you notice they have this part down here. So there's this, let's see if we can find where they've got the base circle is this solid line. So this solid circle over here, that's the circle that created the involute profile with the string and all that stuff, or the tape or whatever. And then you've got this pitch circle with the dash dot line. That is where contact occurs, when the gears are right at this point. This is where the contact occurs. So if the gears didn't have teeth on them, if they were just drums, then this would be the size of the drums that would make contact with another, and just one roller pushing on the other roller. That would be the pitch circle. That's the size of it. And then above that pitch circle, you've got the involute profile. And below it, you've got a slightly different profile over here. And so you've got what's called dedendum and addendum. So dedendum below the pitch circle, addendum above it. So it's possible, the way that the teeth, if you make your gear teeth too long, the spur teeth are too long, that you would end up with a lot of material having to be either worn away or cut away underneath this pitch circle to allow for clearance of the other tooth, maybe the tooth on the gear meshing with the pinion's teeth and the gear's teeth, since they're the same teeth, same type of teeth, would have to be undercut. So they'd have to look like this. So here's here's one involute profile. Let's make the top of the gear tooth. There's the rest of it. So for another tooth over here to interface with this one, you might have to, if it makes this tooth too long, you might have to have a lot of undercut here. And so it creates this little, undercut area, or this waist. And if you make the teeth longer and longer, then you need more and more undercut to make the teeth actually fit together, so they don't crash into one another when the tooth from this one comes in and wants to interface with this tooth. Then it would have to have some clearance. You generally don't want that, and so there's an equation 1311 in your book, and it's a lengthy equation. We'll have to go through it in a second, but it tells you the minimum number of teeth. So minimum number of teeth on a gear that's meshing with a pinion, or vice versa. I think it's actually set up for a pinion. So let's write on a pinion, to avoid undercutting, or I think they call it interference. Yes, interference. To avoid interference. So to avoid this scenario where you undercut and have this really narrow waist on your gear teeth, which will probably make them break off, because the contact force is going to create a bending stress, and the longer this thing gets, it's acting like a cantilever beam, and then the more undercut you need, it gets a thinner and thinner waist, and so you've got a long force cantilevered on a narrow little waist, and the gear tooth will break off. So we'll use this equation 1311 to calculate a minimum number of teeth to avoid this. Let's look at anything else on here. Pressure line. So this line, so this point A over here is where contact begins between the pinion and the gear. And then B over here, lowercase b, that's where it ends. So there's no longer contact between the pinion and gear. And the involute tooth profile will create this straight line between A, P, remember, is when you're talking about they're right in the middle of the pinion and gear, and B, that'll be the pressure line. We've called it the pressure angle. So there are three common pressure angles: 20 degrees, 25 degrees, and 14.5 degrees. Technically, you can have whatever angle you want, but those are the most common ones. And you can imagine that as you know, this would be the 20 degrees right here or right here. I don't know which one this is set at. This might be a 25 degree pressure angle that they've drawn, but the angle is going to create some radial force, some force pointing towards the center of the gear, and some force that is tangential, delivering torque or producing torque. And so the different pressure angles will produce different ratios of tangential to radial force between the gears. And those three are the common ones in use today: 20, 25, and 14.5. We'll use 20 today, just as right in the middle of those two. And again, you could have any you wanted. Let's see if there's other. There's this angle of approach and angle of recess. So that's where the pinion here is beginning to contact the gear tooth, and then at some point it begins to release contact from that pinion to gear tooth. It is possible, in fact, this picture here shows that it is possible to have more than one gear tooth in contact between a pinion and gear at a time. You know, right here they've got contact here and here, so they have two teeth in contact at one time. You at least want to have one, right? So you at least want a whole tooth in contact at any given time on average. But you can have more than one, and there's a contact ratio that describes that, you know, and you generally want that to be 1 or greater, so that you at least have one tooth. If you don't have at least one tooth in contact all the time, then you're going to have some weird scenarios that you probably don't want to have. I think those are the main things to get from here, is particularly the pressure line and the pitch circle. So the pressure line is going to determine the ratio of tangential to radial force transmitted between pinion and gear. And the pitch circle is as if there were no teeth on the gear, they were just round cylinders, then that's the size they would be to just make contact with one another. Your book has a lot of other pictures and diagrams and descriptions of other types of gears, other rack gears, bevel gears, worm gears, all these other types of gears. You need to go and just read about the different types of gears. There are reasons to have all these different types of gears. Spur gears like this, where this would be a spur tooth, are the most common. Let's see. Let's get into how we... Oh, actually, wait. Let's look at this. I printed this out. So, printed this guy. Normally, this piece would be the carrier. It would sit on top, but it covers up a lot, so I took it off. There's a whole bunch of gears in here. So this outer one, this is a ring gear. So it actually has teeth on the inside of it. This is called an epicyclic gear train, where there are some gears like this gear, the one with the red, this one over here. They are going to orbit, for lack of another word, they're going to orbit this gear. And so taking those terms, this is the sun in the middle, and these are planets orbiting it. And this is called epicyclic. Epicyclic meaning that it is there is a gear orbiting another gear somewhere. And so in fact, I have 3 gears orbiting one here. And so this is, let's see, I marked some points. All right, so there's a point. Actually, let's get the red on top. All right, so this one has a gear ratio where if I turn this black gear, well, this black line, which is the sun, and trace where one of the planets has gone, they're not 1-to-1. So that's usually what you're doing with a gear train. Now these gear teeth also, you can probably see right there. These are spur gears, but they're helical. See, they're not straight up and down. They're at an angle. If they're at a helix wrapped, if I kept this going, it would wrap around the center of the gear here. So these are at an angle. Don't worry about that for right now. That's not the point of what we're doing. We're just trying to get our mind around the idea of gears to begin with. So if I make 1 revolution of the planet, so there's 1 revolution, the sun has only moved, up 30-40 degrees, something like that. So another revolution. Now that sun is over here. Another revolution. Sun is almost back to the beginning. And now it's all, maybe it's 4-to-1. I don't know. We'd have to actually measure it to be sure. But it looked like this guy, I had to make 4 revolutions to get him back to the top, more or less where he was. Something like that. And so this is a common setup here to get a lot of torque transfer. You remember there's a radial component. One thing that this does is now all these radial components cancel each other out so that I'm not bending this shaft. The radial push from this gear is canceled by these 2 gears. And so I don't have a scenario where I just have, maybe if these were missing, I think I can take them out of there. Maybe I can. Oh, no, I've got them locked in. So they won't come out. If 2 of these gears were missing, then as this one goes around, that radial component would want to bend this shaft a little bit. So this is one way to avoid that, is just have something to counteract it. So I thought I'd give you an idea of the kinds of things that we're going to look at. In fact, we're going to look at a simple version of this. We're going to look at a ring gear, so the gear on the outside with internal teeth. We're going to look at a planet and a single sun gear, and we're going to ignore the other 2 just to have a simpler scenario. And what we're going to do is we're going to set the number of teeth on the planet and figure out the minimum number of teeth that we can have on, I said the planet. We'll set the number of teeth on the gear, figure out the minimum number of teeth on the planet, and then we'll figure out, the size that we could make this thing. Normally you're trying, well, not normally, but it's often true that you're trying to minimize the size of these components. And so you pick one thing that controls all the other sizes. You're also trying to achieve some kind of gear ratio or reduction ratio a lot of times, to make things the input speed slower but the torque greater. So let's do that, and we'll do that in MathCAD. Actually, let's show what we're gonna model so we have an idea. All right, so we've got, let's use different colors. The sun, let's start with the ring gear, and I'm not gonna draw all the teeth. So the ring gear, a lot of times it's held stationary. That's why I was holding it and turning this one. It's not always. Sometimes it is the part that rotates, but that's not as common as it staying still and everything inside rotating. So we're gonna have our ring gear stationary. I'm gonna, draw something to show that it's kind of stationary here. And then we'll have our sun gear in the middle of that. We'll use red for the sun. We'll make it a little bigger. Well, that one fits, so we'll make it that. Well, no, we need bigger than that. All right, we'll do it this one. There's the sun gear. It has some center of rotation. And then a planet, we'll make a planet green. Let's find one that fits in there good. Or will. That one? All right. So that would be the planet. All right. And we want to set the number of teeth on the sun. We're going to set those to, I think I did 30. Yeah. And we want to figure out what's the minimum number of teeth we can put on the planet gear to avoid that undercutting, that interference thing. So that leads us over to equation 1311. So let's get MathCAD open and work on equation 1311. All right. So equation 1311, I'm going to have to get my book out because it's a lengthy one. I don't remember it all. All right. It says in P. So the number of teeth on the pinion. I'm probably going to have to write this as a definition. It equals 2 times K. We'll talk about what K is. Over 1 plus 2 times, keep writing 8, times M. We'll talk about what M means. We'll do all that in a second once we get it plugged in. Times the sine, I did 8 again. The sine of our pressure angle. We'll use this guy for pressure angle. All that squared. Well, not that, just the sine squared, not the whole denominator. Times M plus the square root of M squared plus 1 plus 2 times M times sine of that pressure angle again, squared. All right, so we got to define some stuff here. First, let's do K. That's easy. K is either 1 or 0.8. So it's 1 if you have full length spur gears, which is common, and it's 0.8 if you have stub, so little short teeth on the gear. We're going to have full size teeth, so ours is going to be 1. M, now M is a little bit of a problem for us, we're going to have to do something with it. M is actually the gear ratio between the gear and the pinion. So the number of teeth on the gear, I used index. Number of teeth on the gear divided by the number of teeth on the pinion, which is a little inconvenient because I'm solving for number of pinion, and I'm going to put a variable in here that has number of teeth on the pinion in it, so I'm going to have to deal with that. Pressure angle, we just set that. Remember, there's either 20, 25, or 14.5, or pretty much the ones you're going to use. We're going to use 20 degrees. All right, so I'm going to change up my equation here, and for M, I'm going to put NG over NP, so the gear ratio of gear to pinion, in for all of these guys. So I'm just pasting it in. All right, so now I've got an equation. It does have the variable I'm trying to solve for in several places. So let us go and see if MathCAD will solve for the number of teeth in the pinion. So I'm just going to try and solve for that. It's thinking. And I get this. I actually get these two. This one's negative. I know I don't want a negative number of teeth, so I want this solution. Make sure I can get all of it on there. All right, that looks like it. All right. So NP equals this. Now we haven't set our number of teeth on our gear yet, so it won't solve it. Let's set those. We set 30. So 30. I'm not going to put 30 teeth, so I'm not literally going to define the word teeth in there. I guess you could. All right, so it solves it. And let's see what it says. All right, it gave us this 14.272 number. We cannot have, well, in a full circle gear, so like we had where they are, you know, on a cylinder or inside a cylinder and there's teeth all the way around, you can't have fractional teeth. if you had maybe let's go back to our deal over here. If you had a scenario where it only, went back and forth and it didn't go around the whole circle, then sure, you only need this little piece of teeth right here. If we're looking at this guy and the sun, then I don't need all these teeth over here if I don't have these planets. And so you could have fractional teeth in that sense if you did some kind of oscillating thing back and forth where you don't ever go past the thing. But if you go a full circle, get back to where you started, then you can't have fractional teeth around there. So in that case, since I do have a full circle, I'm going to define that NP is not 14.272. NP is going to equal, I'm going to use a MathCAD function called ceiling. And what that does is it just rounds up. No matter, it doesn't round like you normally do, less than 0.5, it rounds down, greater than 0.5, it rounds up. It just always rounds up no matter what the number is. So it'll round up to 15. And so what this says is that if I have a 30-tooth gear on the planet, or on the sun, we did that on the sun, the gear, the bigger one, then the pinion would have at least 15 teeth. You can have more than that, but the minimum number is 15. If I have any less than 15 teeth, then I would have some amount of undercutting, and the further away from 15 I get, the more undercutting I would get, and the weaker the gear teeth would become. So I could have a 2-to-1 gear ratio here. Let's figure out how big these teeth are. To do that, I need something called the diametral pitch, and this is the thing I'm going to set. There are other ways to set this, but we're going to use diametral pitch. And what this is going to be, diametral pitch is measured in number of teeth per inch of diameter. Diametral. There is a circumferential pitch that is measured in teeth per inch of circumference, and so you could have that also. So it's pitch is generally talking about the spacing between teeth or threads or something like that. So in this case it's teeth if we're talking about gears. So this would be something like some number of teeth. We'll have 6. 6 is actually pretty low per inch, but we're going to stick with that just so our gears don't get really large. They're going to look, well, I don't know if they'll be this size or not. They'll be a little bit bigger than what we had over here. So this would be 6, and then it would be teeth. I'm not going to write teeth in per inch. And now what I can do is I can go in and calculate the actual sizes of the sun, of the planets, and even of the ring gear. All right, so the diameter of the sun, that's going to equal, the sun is, I think I did this. I might have, when I wrote it the first time, I might have done it backwards. I was calling the sun the center, right? So the 30 gear, NG. So the number of teeth on the gear divided by the diametral pitch. That's in meters. Let's do it in inches. So 5 inches. Obviously, that's not the size that we are using. So in our sample over here, because this is only like 1 inch or so. The planet would be the number of teeth on the. I did P here is not planet. P is pinion. So don't get confused that that's what I'm trying to do there. Like I just did. Diametral pitch. Because I did plus, not underscore. There we go. And let's put it in inches. 2.5 inches. And we'll have to think about this on how to make the ring gear. So the ring gear needs room for the sun. So it needs a diameter of the sun, and then it needs one diameter of a planet on this side, and then, you know, that's more or less like this configuration, right, without these two. And then that same sun would have to be able to fit over here too. So it needs two, I keep calling that the sun, the planet. It needs two planets and a sun that will define the size of the ring gear. So diameter of the ring equals diameter of the sun, the one in the middle, plus 2 planets. (10-inch) ring gear. Now, you probably want to make sure that your ring gear has a even number of teeth, because you don't want a fractional number teeth in the ring, because that would give you, you know, the same problem it would if you had a fractional number of teeth on the sun or the planet. Now it came out to be 10 inches. To figure out how many teeth, you just run this in reverse, right? So teeth on the ring gear is equal to the diameter of the ring gear times the diametral pitch. It does come out to an even number, so that's handy. 60 teeth. Now, if it didn't